So today's topic is actually continuous charge distribution, right? Continuous charge distribution. So I'll tell you what do I mean by continuous charge distribution. See, so far what we have done is we have calculated electric field, potential, etc. for point charges. Okay, point charges, or I would say discrete charges. Okay, discrete charges. So what we mean by discrete charges? You can actually distinguish each and every charge, like say Q1, Q2 here, sorry, Q2 here, Q3 here, like that you can distinguish the charges. Okay, these are actually the discrete charges. Okay, I think I had given some example, like say you have wheat flour. Wheat flour you cannot count one by one, right? Maybe very powerful microscope will help you to find out the particle one by one, but in general we can't, right? But whereas you have a crystal of sugar crystal, maybe you can count, right? So the countable quantities are called discrete quantities, which you can count, but the quantities which you cannot count, those are called continuous. Okay, continuous quantity. Okay, so suppose I tell you suppose you have 4 mangoes. Okay, so 4 mangoes, you can actually weigh them one by one, right? But if I say, so if you ask me to give you some half kg of mango, then I can count 1 2 3 4 how many. I'll just put one by one and see when it is becoming half kg. But if I tell you give me some half kg of wheat flour, so it is not possible to give you by counting 1 2 3 like that. Okay, so for that case you have to take like a pile of that. Okay, a pile of that I have to take in a some bowl or something, and then put in the OM machine. Okay, so by that we have to do. So in this case, look, you might be thinking, sir, what you are talking about this grocery things. Yeah, there is a relevance for this to today's topic, so which I am going to discuss now. So far we have seen, see, we have calculated the electric field and potentials due to discrete charges, discrete point charges. Now what we'll do, now if I tell you I have a wire like this, conducting wire like this, can you tell me how many charges are there? How many charges are there? I cannot tell. I cannot tell. If you tell me, sir, how many charges are there? How many charges are there? I cannot tell you. Okay. So for that case, we have to define one thing called charge density. What is that? Another example I can give you. Suppose I have a sphere like this. Okay, a spherical things. Okay. So if I tell you, like, sphere is suppose a shot football or football, anything, some charges, like suppose some 5 Coulomb is there or 6 Coulomb is there or whatever. So if I just give you a part of it, can you tell me how many charges are there? Part of it, how many charges are there? You cannot tell me. Okay, so another example is, suppose I have a uh, conducting plate, thin plate. Okay, slice. Okay, square slice of some copper wire, copper plate. Okay, slice. So can you tell me how many charges are there? So maybe you can, if you can somehow, if you get the total charge of it, you can tell me that, like, from the from our quantization formula, you can tell me how many electron or how many charges are there. Maybe that is possible. But if I tell you what is the charge over here at this particular position, particular this thing, or what is the electric field created by this thing? Can you tell me what is the electric field created by this continuous? These are actually called continuous charge distribution. So see this line has a continuous charge distribution. This sphere has a continuous charge distribution. This this surface also has a continuous charge distribution. Okay. So today we are learning continuous charge distribution. Distribution. So see, there is actually in our physical world, in our world. So you have always symmetries. Okay, either linear symmetry, line symmetry, or planar symmetry, or spherical symmetry, or cylindrical symmetry. Anything you look in the physical world, there will be certain symmetry. So in the continuous charge distribution, we will be using all these symmetries. Okay. So if we go with symmetry, and if I say that there is a uniform wire, and this actually carrying this wire is carrying charge, total charge Q, and it has certain length lambda, sorry, length L. So what is the charge per unit length? So we have to define some density called charge density. In this kind of continuous charges, we have to define charge density. What is that? Charge density. And for a line symmetry, or for a linear object, we have to define line charge density. What is that called? Linear charge density. Linear charge density. Okay, how to define that? That is defined as the total charge of the wire divided by its length. This is called line charge density, and this is denoted by lambda. It is denoted by lambda. So what is the total charge in terms of lambda? So I'll tell lambda into L. This will be the total charge of this wire. Now for this case, so this has lambda line charge density, and this is a surface, right? This is a surface. So this surface will be having another charge density. How? This total surface, I can break into small surface like this, right? Right. I can just make a small slice like this. Okay. And then if I put all of them together, then I can get the total surface. So in this case, we have to define surface charge density. What is that called? Surface charge density. Surface charge density. And this is denoted by sigma. This is sigma. Some people can write like this also. Okay, this is called sigma. And how do you define sigma? Sigma is equal to total charge divided by area of the charge at this object. Okay. So charge per unit area is called surface charge density, or sigma. You have to remember this notation and the definition also. So in the previous case, it was linear charge density denoted by lambda. Okay, lambda. And in this case, this surface charge density, that means charge per unit area, surface area, and here charge per unit length. Okay, understand? And these two objects, for these two objects, sphere and cylinder, for these two guys, we have to define volume charge density. What we have to define? Volume charge density. That means it has certain volume. Okay, you just take small volume, okay, and put all them together, then you will get a total volume of this. Okay, for this solid sphere or solid cylinder, we define volume charge density. Or any arbitrary object, we actually define volume charge density. With volume charge density, charge, this is charge density. So volume charge density defined as the total charge by volume. That means charge per unit volume, and this is denoted by rho. You might have already seen this. Rho is the mass density also, right? Rho is denoted like mass density is m by v, total mass by volume. So this we have seen in case of our yeah, in our previous class we have learned already mass density. So that is mass by total volume of the object. So here we are defining rho charge density, that is the volume charge density. Okay, so volume charge density, if suppose there is a plate given over here and total charge given, and area also have been given, so you have to find out the charge density. So they may not ask you to find out volume or surface or linear, but you have to know by the symmetry. If it is a planar symmetry, then you have to find out sigma. If it is a line charge, then you have to find out lambda. If it is a volume like sphere or any object, any arbitrary object, you have to find out rho. Okay, rho is the volume charge density. So these are three different types of charge densities we have to define for continuous charge distribution. Okay, look here in your book. Look here. See, in this case, this is the line charge density or linear charge density, whatever. So see, they have taken a small dl length of this wire. So what will be the charge in this? So you have to multiply the charge density with this length itself. Then you get the charge for that particular length element. If you take in surfaces, this is a what this is a kind of lamina. Okay, it is having a surface symmetry or planar symmetry. So in this case, the for this particular patch, see this blue patch, if you have to calculate the charge for, so what you have to do, you have to know the surface charge density and you have to know the surface area for this particular patch. So if that is ds, so you have to multiply sigma into ds, that will be the charge for that particular patch. And you have arbitrary shape, some object, so you know the volume charge density and you know the volume of certain portion of this object. Then if you multiply the volume of that object with this charge density, volume charge density, so what you get is called the that is the charge in that particular volume. So this is what written in your book. You just read one by one. So see, obviously the units are, see, this is Coulomb per meter square and this will be Coulomb per meter lambda. So charge density for linear charge density lambda is actually q by delta q by L. So it will be Coulomb per meter. And here see Coulomb per meter square, because Coulomb is the charge and this is the area. And in this case Coulomb per meter cube. Okay, this is how. And if you just go with CBSE unit, then Coulomb per centimeter cube and all those things will be there. So this is the first part of this. Now see, if we want to calculate electric field for a particular continuous charge distribution, okay, and see that can be done even by discrete distribution also, that doesn't matter. But here what we want to apply is our this knowledge. Suppose a continuous charge distribution in a space has a charge density rho. Choose any convenient origin O and let the position vector of any point in the charge distribution is R. Okay, the figure is shown here actually. The figure is shown here in this. Okay, so from any arbitrary origin, there is a charge distribution and a small volume. Okay, so that is at R distance away, and there is a point P. There is a point P where you have to find out the electric field for this particular charge distribution. So what you have to do? First, you have to actually take a element, volume element, that delta V at R distance from the origin. So if you divide this that particular charge distribution into small volume, then total charge you can get by summing all of them. So, or maybe by taking integration. That depends whether it is discrete or continuous, really continuous object. So look here, the electric field will be, see, total charge actually charged by 4 pi epsilon naught r square, right? So this is a rho dv. So this is for only that part of the elemental volume. This is only for this particular volume, delta V. Now if I want to get the electric field at this point P, due to all, like, hold the object or hold the charge species, then what I have to do, I have to sum over all this small volume. Okay, so rho dv, see, rho dv per, see, divided by r prime square. Okay, that means this r prime also inside the uh, summation, because see, this distance also vary with the this dv, that's why it has been kept inside the uh, summation. So in fact the summation will be rho dv by this, and you can do integration as well. Integration means rho dv into this r square. So actually integration you have to do over rho into dv. R square is constant always for a particular distance, so integration has to be done on rho into dv. So this thing, so this continuous, whatever knowledge you have got here, this continuous charge distribution and all, this will be applying uh, in the following topic, that is Gauss's law. In this case we will be applying this knowledge. So what is Gauss's law? First let us try to define Gauss's law. So Gauss's law actually talk about the flask, the amount of flask passes through. So the Gauss's law states that the flask, total flask passing across a closed surface okay. So okay, closed surface will be equal to the equal to 1 by epsilon naught times the charge enclosed, the total charge, I should say, total charge enclosed by the surface, by the closed surface. Okay, so if I write the mathematical form of this Gauss's law, so I will write the total flask, total flask, that is actually I can write by integration E dot ds, okay, or summation over, you can write even summation, so E dot ds, okay, is equal to 1 by epsilon times the charge enclosed. So I'll write charge enclosed, Q enclosed divided by epsilon naught. So this is the mathematical form of Gauss's law. So if you want to learn this Gauss's law properly, you have to know two things. One is what is charge enclosed, what do you mean by charge enclosed, and another point is what do you mean by the total flask, what exactly you mean by flask. So we had already discussed what is flask, so I'll just tell you for your recap. I'll just tell you what is flask. Suppose I have a surface like this. Okay, Flask is actually the number of field lines passing through this surface, and this surface has to be perpendicular to the electric field direction of the perpendicular. So direct, yeah. So if I just draw a line like this, so say line is perpendicular to. So this, suppose this is a plane. So this plane is perpendicular to the electric field direction. Okay. So if such, see, if this is how, if the electric field lines are passing through it, then we say, so this is flask means flask is denoted by again phi. So that is actually the total number of electric field lines passing across the area perpendicular to the electric field, which is perpendicular to the electric field. Okay, and mathematically we had defined that as E dot ds. Okay, E dot ds, phi is equal to E dot ds integration. Okay, integration phi E dot ds. What is E is the electric field, what is ds? This is the area vector. And I had told you that time, what do you mean by area vector? So if this is the area, outward normal will be the area vector. So this is ds n cap. ds n cap. ds is the magnitude of the area, and n cap is the direction of the area. So area vector can be even written E dot n cap ds. So this is a scalar quantity, this term magnitude, and this is the direction is the actually vector. This is a unit vector along the direction of the along the direction normal to the area. Okay. So if I say my area is like this, so my normal will be like this. Okay. So if I suppose I have two surfaces like this and another surface like this, so what will be the outward normal? Outward normal will be this way, and for this guy outward normal will be this way. Okay, this is called outward normal. Okay, suppose I have, see, I have a cube, right? I have cube. So what is the outer normal for this surface? This is this way. What is the outer normal for this surface? This is this way direction. For this will be upward, and for this guy it will be this way. So that is the outer normal. This is unit vector for this, and for this surface this is the unit vector. Okay. So ds will be like that. Okay. So what you have to take? You have to take the normal direction. That means if suppose the electric field sometime is making certain angle, this is suppose the n cap ds, and this is electric field. So your flask will be, so the electric field component has to be in this direction. So if suppose this is the angle theta, so you have to take E cos theta. Okay, this will give you the flask. Okay, E cos theta into ds. This will be your flask. Okay, this will be your flask. So the component along the direction of the outward normal of the area vector or the plane area of the surface. So that will give you the flask. So you look, so this is, that's why it is written as E dot ds. Okay, if I suppose I have this surface, so electric field is passing through like this, perpendicular to this. I have taken a small area ds, and that is what I have written over here. And if I integrate, that means I am just summing over all. And ds, why I am integrating? Because this is a continuous quantity. That's why I am integrating. Otherwise, I can write even with the summation. E dot delta s. Okay, I can sum all also. I can take summation. So this is a continuous charge distribution, like whatever we have taken. See the line charge, okay, that I have taken, and then I have taken this. These are continuous. So surface area I have taken, volume sphere of the volume I have taken. Okay, so yeah, volume of the sphere we have taken. So these are continuous charge distribution. So for that case, we have to do the integration only. Okay, now look, we'll just see from your book what is Gauss's law. See, look here, as a simple application of the notation of the electric field, electric flux, let us consider the total flux through a sphere of radius r, which encloses the point charge q. Suppose our point charge Q is actually inside the sphere or at the center of the sphere. Okay, at the center of the sphere there is a point charge Q. Now what they are doing, they are saying that how many field lines are passing through this surface normally. Can you tell me? See, so this will be going, say field lines going outward normal, right? It will be radial. Okay, let me just take this figure. I'll copy this figure and then show you. What they're trying to say is, suppose this is my point charge Q, which is there inside the sphere. Okay. Now, if I want to calculate the flux through this is a closed surface, right? This is a closed surface, spherical surface. So this is the spherical surface. So you have to find out the electric field lines like flux, total flux through it. So how to calculate total flux through this closed surface? How to do that? So you have to see, we have written EDS, right? EDS. DS. That means you need here E n cap ds. This you have to write, isn't it? That means what you need to know? You need to know the direction of the electric field as well as the direction of the element of the surface you take. Okay, that you have to find out. Suppose I take an area element on the surface. So suppose I have a sphere, so I just cut a portion like this. Okay, so this is the area element ds they have taken. This is the area. So this is the area they have taken, right? ds area they have taken from this total sphere of radius r. So look here, what is the normal to the surface? Normal to the surface is this way, see, which is shown over here. And how electric field is actually, which direction is like which direction the electric field will be? For a point charge, always for a point charge, always electric field is radial. It goes radially outward. Do you remember that? Radially outward. That means, look, the unit vector for this area element or the normal to this area and the electric field are in the same direction, that is the radial direction. That is the radial direction. Okay, that is the radial direction. That's why they have written here the ds and electric field is in the same direction. So I can write E dot ds in place of E dot ds. So what I can write is E ds cos of 0. That means EDS. Okay, EDS. So you might be thinking, sir, why you are writing U? Sorry, E is the electric field, but that electric field, whether that electric field is like total electric field for this small area also is the same. Electric field, we know electric field created by this charge small q is maybe E. You can write q by 4 pi epsilon naught r square. That is very nice. But how come it is? Because it is the electric field through this also, this small area. Now look, the electric field, see, as you can see from here, it depends on the r, and on the surface it will be everywhere, it will be the same. On the surface at this particular point, electric field E is equal to this one. If I would have taken another surface area, okay, like this, okay, like this. So this, through this also electric field will be, so this is suppose ds1. So electric field will be the same because it depends on only on the r, and r is same magnitude. So this r is r, this also r. So this is from the center to the sphere, the distance is same. That's why the electric field is same, or I can say constant. It has a constant value and always perpendicular to the surface at any point. Perpendicular to the surface at any point. That means the surface and electric field are in the same direction. So I can write in this way. Now if I want to calculate the total flux, so what I have to do, I have to write E EDS, right? EDS I you have to take sum over I. Okay, that means see DS1 I can write DS1 plus EDS2 EDS3 like that, delta S3 like that I have to write for all the surfaces. What if I am taking all of them, you have to write like that. But since it is actually continuous charge distribution and uniform charge distribution is there, then I can actually define this charge distribution as rho, and I can integrate it. If I want to know the total charge, I can integrate it. Actually, I can write rho dV. And if I want to write the flux, also similarly, I can write total flux will be E dot ds like this. Okay, and I can see if I write ds, so E is constant, so E will come out, and only integration you have to do on ds. So ds integration means total area of the surface. See, total surface area of the sphere. What is that? That is nothing but 4 pi r square. So I can write 4 pi r square. So what is the total flux then through this surface area of the sphere? So that is E into 4 pi r square. Now what is the charge enclosed? Here the charge enclosed was how much? Q, small q, and divided by epsilon naught. This is the Gauss's law. So what is the Gauss's law? The total flux passing through the surface, closed surface. So total flux through the closed surface is equal to 1 by epsilon naught times into the charge enclosed by this closed surface. So charge enclosed by this closed surface is q, right? Small q. So that is what I have written. So see, the mathematical expression for the Gauss's law was this. And from here, see the left hand side, E is constant. I have taken out integration ds. I have got 4 pi r square. And right hand side, I know the charge enclosed is the small q by epsilon naught. This is q enclosed. Okay, enclosed. So this is how I can find out the electric field at any point on this surface. Look, the electric field will be q by 4 pi epsilon naught r square. Look, this is the electric field we have calculated for a point charge, right? We know this is the electric field for a point charge. So this is how, when you don't know, like when you know the symmetry of any charge distribution, electric field at any distance r, you can find out by the use of Gauss's law. You can use the Gauss's law to find out the electric field, but in that case, you need to know the symmetry. Here, see, we have written the area. So why you need to know what you need? You need to know the symmetry, because the integration ds you have to do to calculate the total flux. So that integration you can do when you know the surface, symmetry of that. Okay, if it is cylindrical symmetry, then you should have written pi r square L. You should have written this. If it is square symmetry, you should have written A into B, something like that. Okay, so this is what you have to take care. Now let us see. So I don't know whether both of you are understanding. Can I get your response, Nikhil? Are you understanding? What is the total flux and how do we calculate? Do you understand? See the total flux through the area element is this way. Okay, and the total flux they would be showing over here. Look here, the total flux is summation over delta S means total area, that is pi r square. So look here, the electric flux through a closed surface will be always equal to q by epsilon naught. This is the actually this is called this is the statements of the Gauss's law that I have already told. The flux, total flux through a closed surface. Okay, total flux through a closed surface will be equal to 1 by epsilon naught into the charge, total charge enclosed by the surface. Okay, so do you understand this? Do you understand this or not? So this is Gauss's law. We are just trying to see another symmetry, cylindrical symmetry, suppose. So this you have to understand properly. So this is a cylinder, okay? Cylinder has how many surfaces? Three surfaces. Two flat surfaces and one curved surface. Okay? And look here, the electric field is along the axis of the cylinder. Along the axis of the cylinder, okay? That means it is passing through perpendicular to this flat surfaces. Now, if you want to calculate the flux through it, can you tell me what will be the flux through? Suppose the area is both cases area is S. Suppose this is S1 and S2. Obviously, S1 is equal to S2 only for a cylinder. So, can you tell me what is the flux through this due to this electric field which is passing through this?
Zero, sir.
No, flux through S1 is not zero. See, suppose this is along x-axis. So I'll write E dot n cap S vector, right? So suppose S1. So what is the n cap direction? It is minus. See, it is x-axis means it will be minus x cap, right? See, outward normal for this surface will be this way. This is minus x cap, okay? So that's why I'll be writing. I see. Okay, so my surface is minus x cap. This is x cap direction. E is x cap direction. So that will give you minus, right? Minus ES1. Do you understand what I'm trying to say? Here the electric field is this direction, x cap. And my area has S1 in x cap minus x cap in this way. So this will be giving x cap dot x cap. One is minus sign. So this will give minus one, right? So what will be the flux through this S1? The flux through this will be E minus S1. Okay. What is the flux through this? Nikhil, you have to tell
One,
me.
sir.
Yes. Tell me. No, no, not one. E, see, S is the area. I have to write E in cap. That is the area normal. S2. Now you have to tell me what is the direction for this and what is the direction for this. Then you have to tell me here, see, electric field in this direction. So that is the x cap direction. What is this? Area normal has direction x cap as well, right? So I'll write E into x cap dot S2 into x cap, right? So E S2 and x cap dot x cap. What will be the result? From here, you will get 1, right? So what you get? Phi is actually this is S2. This is phi E S2, right? Right or wrong?
Yes, sir.
So do you understand this? And so you can tell me what is the total flux then because of these two flux surfaces, phi 1 plus phi 2, it will be 0. If I say S1 is equal to S2, if I say S1 is equal to S2, then see this is also S, this is also S. So ES plus ES minus ES. So if I write this is minus ES and this I can write plus ES because for a cylinder you have the same surface, right? Area for this flat surfaces. So what will be the total flux through these two flat surfaces?
Zero, sir.
0. That means it is not enclosing. It is actually not enclosing any net flux because of these two. Actually, net flux is 0. And in another way, I can tell you, like, see, the electric field lines are entering here and exiting here. That's why there is no flux. Okay. The number of field lines entering here and number of field lines exiting here are the same. That's why they are the net flux will be 0. Net flux will be 0. Suppose I have a flat surface like this and like this. So here there will be net flux. Okay, the number of field lines entering to here may not be the same number of lines passing through or exiting here. Okay, if this is the case, you would have got. But in this case, the surface areas are the same. That's why the flux, net flux could be 0 due to these two flat surfaces. Now I look what is the flux through the curved surface. Again here I'll write E dot ds, right? E n cap ds. Tell me what is the n cap direction for this? This is a curved surface, right? So it will be perpendicular to this, means this way, right? This is the n cap, right? Do you agree with me or not? This will be like this, n cap. So what is the electric field direction? Suppose this is y and this is x. Okay. Now what is the angle between them? If I write
90
y cap
degrees, sir.
and 90 degree, what will be the dot product? What will be the dot product then?
0,
Suppose
sir.
it's 3 and this is y cap 0. So what is the flux through the curved surface? That is also 0. So in this case, then can you tell me what is the total flux through this closed surface? What is the
0,
total
sir.
flux? Phi 1 plus phi 2 plus phi 3, total will be 0. So flux through this will be 0. So this is what they have told you. So so you can see when the electric field is actually along the axis of the cylinder, in that case the total flux through this cylindrical closed surface will be 0. Okay, that is what is written in a book. You can just read it. Okay, look here. So it is here. Okay, you just see that. And now look, now I will tell you how to see Gauss's law has certain. See, you tell me, like, see, you have learned already that the Gauss's law is Gauss's law Gauss's law is actually total flux, okay, which we have written E dot ds, okay, is equal to charge enclosed by epsilon naught, or epsilon naught times the charge enclosed by the closed surface. Okay, so to apply Gauss's law, how to apply this Gauss's law? To apply Gauss's law, first of all, you need to know the symmetry of the charge distribution. Symmetry of the charge distribution. Okay, whether it is a spherical or cylindrical or planar, whatever, that you have to know first. That's why otherwise, see, this area you will not be able to write if you don't know the symmetry. Then you need to know the total charge enclosed by the surface. Now look, when you go for applying Gauss's law, we have to draw a Gaussian surface. We have to draw a Gaussian surface. We have to draw a surface enclosing the charge. Suppose I have a point charge. So point charge, how electric fields are going out? Radially outward. So what it has? Which symmetry it has? Which symmetry do this electric field have? See, it was 1 by r square, right? Proportional to 1 by r square. So what symmetry it has? What symmetry it has? Spherical symmetry, right? What is that? Spherical symmetry, right or not? It is a spherical symmetry. So if you know there is a certain symmetry, suppose I have to see, if you are asked that there is a point charge, capital Q, you have to find out electric field at r distance away. So what you have to do, you have to draw a Gaussian surface, like enclosing this. Suppose this is the r distance, so enclosing this charge. So you have to immediately draw a surface like this. That depends on the symmetry. If it is spherical symmetry, so you have to write a spherical surface around it, okay, whose volume is actually enclosing this charge, point charge. Okay, understand that or not? Hope you understand. So you have to
Yes.
draw a surface. So this surface is called Gaussian surface. Okay, Gaussian surface. And what you have to do, you have to find the flux for this Gaussian surface. So whatever flux we were calculating, that flux has to be, that has to be through this Gaussian surface, and whatever charge enclosed, that charge has to be enclosed by this Gaussian surface itself. Okay, volume of the Gaussian or closed surface, this Gaussian surface. So do you understand what is Gaussian surface? Gaussian surface is the surface which we draw, okay, according to the symmetry of the charges while calculating the total flux. Look here, the significance of this law is that it is true in general and not only for the simple cases we have considered above. Let us note important points regarding this law. Gauss's law is true for any closed surfaces, no matter what is the shape and size. Okay, that does not matter. You can draw it, like you can take any arbitrary shape and size of the matter, but for that case you have to define a particular symmetry. Okay, and for that case it will be easier. So now this Gauss's law, which I have written q by epsilon naught, actually this include actually the charges, all charges. Actually this is not only applicable for continuous charge, it can be applicable for discrete charges also, Gauss's law. So if you have many charges in this Gaussian surface, see I have taken only one q. If I draw, if I have any other charges like q1, q2, q3, everything in this Gaussian surface, then on the right hand side I have to write not only q, I have to write q1, q2 plus q3 plus q4, like that. The total charge you have to write on the right hand side, whatever charge is encloses inside it. Now there will be a situation when the Gaussian surface actually you cannot consider any charge on the right hand side of the Gauss's law which is outside the Gaussian surface, and this Gaussian surface, but in that case actually the electric flux will be for both. Okay, the electric flux will be for actually both. Okay, both the charge inside and outside. The electric field, see, electric field whose flux appears on the left hand side is due to all the charges both inside and outside of the surface. So what I mean to say, suppose you have certain charges q1, q2 and q3, etc., q4, like that. You have certain charge distribution. So you are just taking a, suppose, spherical symmetry, and you have drawn this is a Gaussian surface, Gaussian surface. Okay, now look, you have to write eds, e dot ds is equal to q enclosed. So q enclosed you have to write q1 plus q2 plus q3, okay, q3 plus q4, all divided by epsilon naught. This you have to write. Now if you have any other charge, suppose q5 is here outside, so the flux here is not only for the electric field which is created by this pore, it is actually due to this also, due to this also. Okay, due to this also, this also will create electric field, right? For this also the flux will be due to this also, but only one thing is there, only one thing is there, this will not come into the right hand side, because see the electric field lines, whatever field lines coming out, see, in coming in, they are all going out, actually all going out. See, they are going out also, that's why why. So whatever flux they create, actually that will not be in this actually conceptually. Okay, but see the electric field they create, all of them, the flux is due to all of them. But see, this flux will be whatever entering, that is what is actually going out also. So if I draw another figure like this, so suppose there is a charge here outside. So look here, this is the solid angle it makes. See, in this case, see the area normal is actually this way, and for this case area normal is actually this way. Okay, this way. And if this look here, if this area actually the same, then the flask will be actually uh, flask, whatever flask enters, that will go out also. Okay, that's why the external charges will not be counted in the right hand side. Okay, see in the situation when the surface is chosen, that there are some charges inside and some charges outside, the electric field is due to all the charges, but both out and inside. Okay, the term q on the right hand side in the Gauss's law, however, represents only the total charge inside the area. That is what I wanted to say. Now the surface that you choose for application of the Gauss's law is called the Gaussian surface. You may choose the Gaussian surface and apply Gauss's law. However, take or not, let the Gaussian surface pass through any discrete charges. That means if you have a Gaussian surface through a charge, this so actually it should not happen. Actually, you should not take a charge just on the boundary of the surface. Okay, you cannot take that. This is because the electric field due to a system of discrete charges is not well defined at that location. Because as you go near to the surface, the electric field lines will be infinite. So I'll tell you what it is. Suppose I have a charge over here. Okay, this is point charge, and you are drawing your Gaussian surface. I have some charges inside as well. I'm not drawing them. Okay, I'm drawing a Gaussian surface like this. Okay, so this Gaussian surface, look, it is not a properly drawn. It is not properly drawn. Not properly drawn. Why not properly drawn? Because we cannot take the electric field. Like electric field is not defined for this particular charge. When you draw on the surface, like when you draw your Gaussian surface through that charge. Why, like q is actually sorry, electric field is q by 4 pi epsilon naught r square, right? R square, right? So see, as you uh, so your surface will be, see, your distance is, see, so this distance is charge from charge to the surface, right? If my charge is here, this is the r distance. If the charge is near, see, on the surfaces, so this is actually very close to the your surface, very close to the surface or on the surface, then actually it is going to almost going to zero. So that means what? The electric field actually going to infinity. That means you don't have, so electric field actually blows up. It called blows up to infinity. Okay, blows up, and it will not have a finite value. It is infinite. Blows up means infinite, and infinite. So in physics, infinite quantity actually, that is of so this actually should not happen. Actually, a physical quantity, any physical quantity should not be infinity. It can be a zero quantity, but it cannot be infinity. Okay, infinity, any physical quantity cannot be infinity. So we should not take our Gaussian surface such that any discrete charge is just falling on the surface of that. That we should not do. And then Gauss's law often useful towards a much easier calculation of the electrostatic field when the system has some symmetry. This is facilitated by a choice of suitable Gaussian surface. Actually, when there is certain symmetry, this will be more useful. Finally, Gauss's law is based on the inverse square law dependence. Okay, inverse square dependence. And if in in any cases by Gauss's law we are not getting the inverse square dependence of the electric field, whatever electric field we are calculating from the Gauss's law, if we are not getting inverse square dependence, then you have to think that you have applied the Gauss's law wrongly. Okay, so these are the points. You just read it first. If you don't understand, next day I'll ask you what are the meaning of these points. Okay, better you read and think a while. Okay, if you can't understand, I'll tell you again on the next day. Now let us do one simple example. I'll just copy this problem just to avoid to see the uh, solution. I'll copy this. I'm sorry, just a minute. Just a minute. Okay, so I'll just take a snapshot of this problem. Okay, so this problem says that the electric field components in figure this are see along actually x direction. Electric field components are along x direction. See this way. So the electric field is varying E is equal to alpha x to the power half, x to the power half. Okay, in this manner the electric field is varying. Okay, so you can see this is varying in the x direction. An electric field component along y direction and z direction is 0. Okay, now you have to see in which alpha is given already. Alpha value is given. This is 800 per 800 Newton per Coulomb meter, Coulomb per meter per half. Anyway, so yeah, so this is given. Calculate the flux through the cube. You have to calculate the flux through the cube. So this is a cube, right? Calculate the flux through cube and then the charge within the cube. Okay, you have to calculate the charge within the cube. Okay, can you calculate the, see here you might be thinking, sir, how do I calculate the charge? So just remember here we are going to apply the Gauss's law. So E dot integration E dot ds, okay, is equal to q by epsilon naught. If you know this part, then epsilon naught is a constant value, so you can find out the charge right inside that, isn't it? If you know this thing, this flux, if you know the flux, see which we have to calculate through the cube, then you can find out, after finding out the flux, you can find out the charge here. Okay, so I think, yeah, can Priyadarshini, can you tell me what is the flux through this cube? Even Nikhil also can tell me. So what I'll write, summation E delta S, right? E delta S. Okay. Summation E delta S.
Yes, sir.
Okay, let us take that. Let us see from just take this surface, left hand surface, this surface first. So this is suppose leftmost surface. So what is the flux there? if they have given, see the area, the sides are given for the cube, so area will be obviously a square. Okay, a square with the area. See the electric field direction. Electric field direction is this way. So what will be the flux here? Suppose flux left hand side L. What will be the flux? I have to calculate the flux through all the surfaces. I have to add them. Thereafter, then only we will get the total flux. So what will be this? I need to know the area vector direction and electric field vector direction, right? Then you have to take the dot product. So what is the direction of the electric field? Along the x cap direction, right? Right or no? So what is that? What is the electric field? See, the normal for this phase is this way, right? So this will be electric field is x cap direction, but your area is whose direction? Minus x cap. So this will give you minus value, and obviously parallel. These are anti-parallel. So you will get, what you will get is E into the area, right? A square. And in this case, see the electric field also, you have to see electric field here. How much is the electric field? What is the value of x over here? What is the electric field? What is the value of x here? So electric field is varying like this. Previously, you can tell me alpha x to the power half. So what is the electric field at this surface? So this is the distance of x, right? You have to write here alpha into a to the power half. This will be your electric field. Okay. So then you will have minus sign over here, and this will be alpha, and it is how much? 5 by 2, right? It is about 5 by 2. Do you understand that or not? Okay, look here. When see x is equal to 0, electric field is 0, right? Here electric field is 0 here. What is the electric field over here? Electric field is, you have to put the value of this distance, okay? And what will be the electric field for this surface then? Here,
0, sir.
where it will be 0 for this surface, electric field.
Yes, sir.
Is it 0 for this surface? It is a plus 2a, right? See this much a, and from here another a here, so it will be 2a, right? 2a to the power half. Okay, this will be the electric field on this surface. Okay, and you have to again multiply a square. Understand? And here, see the area normal is this way, nx, and electric field also in this way, ex. So they will be giving you only 1. Dot product will give you 1. Here minus 1 dot product. And see other surfaces, see this surface is actually perpendicular to the electric field, so there will be no flux through this. So this surface also, see yz direction, there will be no field, no flux. Only flux will be there through these two surfaces. Okay. So then you have to get left and right only. So left plus right. So this will give you total flux. Okay, this will give you total flux. But up, down, and two sides they will not give, because electric fields are not there. See Ez and Ey was given 0. Okay, alpha value you have to put properly, then you will get the value of the flux. Okay, you have to take here, see minus alpha a to the power 5 by 2. Here it will be plus 2 root 2. Okay, root 2 alpha. Oh, alpha also was inside. No, alpha, and then a to the power 5 by 2, right? This is the thing. So you have to, so you'll get something like the 0.41, like that, alpha a to the power 5 by 2. So alpha, if you multiply, you will get the value of the flux. So then you just apply Gauss's law. So total flux is equal to how much? Q by epsilon naught. So you just multiply epsilon naught into 5, you will get the charge enclosed in the cube. Okay, look the solution here in a book. Look here. So see, since the electric field has only x component, so the surfaces perpendicular to x direction will have no flux, right? So zero flux. And then see, the left hand side, the electric field is actually alpha a to the power half, because it is x dependent, right? X dependent means alpha x to the power half. So here you have to see x direction, how much distance it has gone. According to that, the flux will be. So this surface is actually a distance away from the origin. So the electric field alpha a to the power half. And this surface, right hand surface, this one is 2a distance away. So the electric field will be alpha into 2a whole to the power half. Okay. And look, for the first case, for the first case, the area normal, outward normal is left hand side. That means minus x cap. So the flux will be minus for the first case, and in right hand side case, the flux will be positive. Okay, so you have to, yeah. So you'll get something like this. Okay, if you just, yeah, if you just multiply this, you see a was given 0.1 meter. Okay, 0.1 meter. So if you just put the values, you will get the flux. After getting flux, you have to multiply the flux with epsilon 0 by the Gauss's law, right? F is equal to, see, total flux is equal to Q by epsilon naught. So if you want to know the charge enclosed by the cube, so that is phi into epsilon naught. This is how you can solve many problems. We'll see the application part of the Gauss's law on the next day. Okay, next day you just see up to this portion. Okay, this example you read up to this example, and next day we'll finish this chapter. Okay, we'll see the application part of the Gauss's law and we'll finish this chapter. Next day we'll finish this chapter. Okay, or shall I do one application today? I think you just read up to this today. Okay, then we'll see next day we'll just, yeah, next day we'll finish this chapter. Okay, so is that all right?
Yes, sir.
Okay, you read up to this point. This point. Okay. So next day we'll see the application of the Gauss's law, and we'll finish this chapter. We'll, yeah. If I have to take, see, next day Sunday. So if I have to take for 15 or 20 minutes extra, I'll take, but I'll finish this chapter on that day. Okay. I don't want to drag again. So you be prepared for extra some 15 or 20 minutes. Okay. So 6 to 7, that means it may go to 6 to 7:30. Oh, okay, 7:20, 7:30. Will that be okay? Or you have some other classes after that?
No, sir.
What about Nikhil? Nikhil, do you have class?
No, sir.
Okay, then Sunday we'll finish this chapter. Okay, if I have to take some minutes extra, I'll take and I'll finish this chapter. Okay, then we'll see if we'll take up some examples also, like in the next class related to this Gauss's law. Okay, okay, then see you on Sunday. Bye.
Thank you, sir.
Thank you, sir.
Okay, welcome. Yeah.